All right, so this is our review of linear algebra, part 1. Okay. So I posted the slides. So far we went over basically the course highlights and how are we going to deal with various rules in the course. And also I introduced the course in the last lecture. And today we are starting linear algebra review. So this is part of our lecture 1. So basic motivation for review of linear algebra is that linear algebra provides tools for dealing with arrays and doing computation with arrays. And by arrays, I mean 1D arrays, which are vectors. So one dimension means that I just have like a sort of either a column or a row of numbers. Or 2D arrays, you all are sitting basically in a two-dimensional array in this classroom. And of course, you could actually now stack up things into 3 dimensions as well. Visualizing something beyond, well, this 3-dimensional array could change in time. So every time snapshot, let's say every second, you could have a different 3-dimensional array. So we can actually visualize how things change in 4 dimensions, but beyond 5 dimensions, it's kind of hard to visualize the arrays. But mathematically or on computers, arrays could be 5-dimensional, 6-dimensional, and so forth. It's just extremely hard to visualize how more than 4 dimensions actually behave in space. Now, linear algebra provides tools for manipulating these arrays. Now, let's work in pairs. Or 3 people, 2 or 3 people at a time, doesn't matter. So each group of 2 or 3, I want you to come up with arrays in petroleum engineering. What are some of the arrays of data that you can come up with in petroleum engineering? So let's take a minute or 2, you can discuss in, again, groups of 2 or 3 people. And let's see what we come up with. And think about 1-dimensional and 2-dimensional arrays. So let's see the next person in blue. What did your group or cohort come up with? Pressures, temperatures. So when I say it's an array of numbers, let's say that I have pressures that are pressure 1, pressure 2, pressure 3. What does this 1, 2, 3 mean? What does it correspond to? So if I was, for instance, in the lab, I would have a core, right? So then I would measure pressure where I have a pressure tap. So it's a physical location along the core, right? So I might have like I have inlet and outlet, and I might have, for instance, 3 to 5 pressure taps along the core. So I would get an array of pressures, and that array of pressures could change in time as I go along, right? And those are my pressure 1, pressure 2, pressure 3. Now what's your next example? Temperature, similar thing. If I have, wherever I have a sensor for temperature, that's where I have a point, and those could be either in 1 dimension or in 2 dimensions, right? So I could have different temperature measurements, all right? So let's actually move on to the next person in blue. So can you come up with any other? Did you come up with any others, or your group? Examples? What are the longest? Is your shirt blue? Just kidding. I'm talking actually to the blue shirt behind you, but we'll get to you as well. Our next color is gray. Anyway, what are some other examples? Production data. So those are typically in over time, right? I have a point. So those are basically each element of the array basically corresponds to a time point when I got the measurement. And those are typically production is at wherever my reservoir is. What happens before production? We drill a well. After we drill a well, what do we do? Can you chip it? After drilling a well, what kind of measurements do you do? Measurements. Well logging? Well logging? What does well logging do? So basically, in any type of well logging, you will send a sensor, and how many different measurements you will do depends on how much, what's your budget, okay? You can go on and on with the budget. So then basically, along the length of the well, you will record something. So if you're measuring porosity, there's a neutron tool that says like neutrons essentially, that scatter and come back, and based on what comes back, that is, you compute the porosity. So essentially, you will get a porosity measurement along the depth of the well. So for depth point, typically every foot, you will get a number. So you'll get, those are the largest numbers, one-dimensional numbers, because you go every foot up to 5,000 feet, 10,000 feet, okay, depending how deep you go. If you're in unconventional, we're gonna go to 10,000 feet, and then we'll go horizontally. So those can be very long strings of numbers. And those are vectors, right? And you have to process them as vectors. Now you could have any other well logging measurement as well. It could be resistivity, it could be permeability, it could be all kinds of numbers that you could get in this array, and those are vectors. Does anybody have an idea of a two-dimensional? Yes?
Maybe like going down horizontally and then horizontally fracking, or going down vertically and then horizontally fracking.
That's one dimension and then again one dimension. So it's still kind of one-dimensional. Any other ideas? Good attempt though.
What about like a reservoir down underneath the surface? Is that 3 dimensions because it's volume?
This is actually a picture. This is a simulation. But this is simulation of an entire reservoir. This is actually permeability, I believe. Okay? So I could have in simulation of a reservoir, my reservoir is a 3-dimensional entity. Okay? In the simulation, I will very unlikely have measurements like this. Not very unlikely. I do not have measurements, 3-dimensional measurements that cover this entire region. So these colors are a product of a simulation, but this is a 3-dimensional array of numbers. And each color is actually sort of between whatever is my minimum and maximum. Okay? I get the 3-dimensional array. There is another 2-dimensional, has anybody heard of a borehole televiewer? That's an image. So image basically you get, as a log, you get like an image of grayscale values. I didn't put it on my PowerPoint, but I will. But basically you get grayscale values and you get the idea this tool is basically imaging your cylindrical well, right? So you get for this, on the inside of a cylinder, you get an image, and basically based on the grayscale value, if something is really dark, you know there's a fracture there. Or something happened to the well, typically there could be a damage near well, so you will actually see a very dark color. And if your actually side of your rock is intact, then you will actually just get normal sort of lighter grayscale values. So that allows you to see, well, what is the extent of damage? And did you actually intersect the fracture, or did you cause fracturing of the well? Okay? So you can see that, and that's a 2-dimensional image because you actually get along the sides of the cylinder, so when you spread it out, you have a two-dimensional array of numbers, because each grayscale value is actually a number. Or you could color it in any way you want. You could color it this way too. So that's the image. There could be some imaging around of the cylinder, and essentially that could provide you with a two-dimensional image. Any other? Sure.
What is the difference between processing a one-dimensional vector like porosity, where like you've got the porosity value and the location, versus processing it as a two-dimensional scalar, like where one dimension is the porosity and the other dimension is the location?
So you could actually, so the good point, technically the way information travel, you could just have porosity measurements, but then you would have to know the depths that are associated with it. Or you could put them in two columns, okay? And in one column you could have the depth, and in the other column you could have porosity values, or any other, resistivity and so forth. So actually your entire, whatever it is that you measure, could travel as a multi-dimensional array. I agree.
So why
So that's your design. Or typically there are standard files in .las files that actually record certain things, and all of those matrices are recorded. Okay. Any other questions? Any other examples that you'd like to mention?
Compositional analysis. What would compositional analysis do? Just one array?
Well, compositional depends on how many components you're tracking. Okay, so you could have actually multiple components, especially
Like methane, and each one would be its own array.
precisely. So there are multiple possibilities, and there's a point well taken is how you arrange the data depends on you or some accepted standard in the industry. Okay, so that's something that typically has to be agreed upon. All right, so those are our examples, and actually we will see those examples in our homeworks. So what are the objectives of this particular review? We're going to figure out how do we do basic subtraction, addition, multiplication of vectors and matrices. And we will initially do very small examples, but we have to learn on something. Bear in mind that you will actually apply it on something that is larger later. And basically we'll just do standard math that is done with these matrices. We will calculate, for instance, inner dot product, calculate norms of vectors. We will define these, and we will try to compare two vectors. And we will do this both by hand and using MATLAB. If you would like to read, technically most what we will cover is in these slides, but if you would like to read the text, then there is a matrix algebra overview, which is chapter 8.1 in the textbook. Okay? So vectors, so this is now formalizing what I mentioned. So I will either have a column of numbers, or I will have a row. Again, which one I use is often up to me, okay? But I do have to use them correctly so that the math is correct. We will get to that in a moment. So for scalars, or scalar just numbers, which are 1, 2, 3, and so forth, we will use lowercase Greek letters, alpha, beta, gamma, and so forth. For vectors, we will use lowercase Roman letters, such as U, V, X, Y, just like we have here. And for matrices, we will typically use uppercase letters, so just to be able to distinguish them all. Okay. So here is an example of operation. If I have two vectors here, so I have the first vector, which is 2, 1, 0, and the second one, which is -1, 1, and 5. What's the most natural way to add them up? What is my next blue shirt? I have one more blue shirt to target. Corresponding positions, right? So basically it's going to be in the first row, it's going to be 2 minus 1, so it's going to be 1, okay? So in this position, I'm going to have 1. In the second position, I'm going to have 2. And in the third position, I'm going to have 5. So I have to have matching number of positions in order to be able to perform this operation, okay? So essentially, addition and subtraction kind of happen naturally, and you involve corresponding elements and perform the information, the either addition or subtraction on the scalars that you find in those locations. Now, if I was to multiply one of these vectors with a scalar, let's say that I want to multiply this vector 2, 1, 0 by 2. How would I do that?
Just multiply each.
So you would go each. You wouldn't just multiply first one and say 4, 1, 0. You would go with 4, 2, 0. Basically multiply each element by the scalar you want to multiply. So if I find a scalar in front of this vector, I'm going to multiply each element of the vector with that scalar. And then there's a transpose operation. Basically, transpose operation creates a row vector from a column vector and a column vector from a row vector. So I'm just flipping them back and forth without changing the numbers. So essentially, here, if I had this vector x1, x2 all the way to xm, which is a column vector, transpose of this vector would be a row vector with these same elements. So it would be a row that has x1, x2 all the way. So this is a row, this is a column, right? So I would have x1, x2 all the way to xm as a transpose of x. And if I was to transpose this y vector, I would get a column vector from a row vector. Okay, so it's just flipping things from a row to column and the other way around. Okay, so those are some of the basic vector operations. And then when I kind of put them all together, I could have a linear combination of two vectors. Okay? So if I had a scalar alpha and scalar beta, and I had two vectors u and v, I can get a linear combination alpha u plus beta v, essentially by multiplying each element, let me use the mouse, each element of u by alpha, and multiplying each element of v by beta and adding them up. So my result would be alpha u1 plus bv1. That would be my first element. Then my second element would be alpha u2 plus bv2 and so forth. Okay? So it's sort of in a natural way. So here are some examples. We said gray shirts, right? All right. So how would you perform the first operation?
Well, we first multiplied the second vector with the scalar, so let's make it -3 and 3.
Okay. So basically, when I perform this operation, I would have -3, 3, and then I add them up. So my ultimate result would be plus 2 minus 3, which is, and 1 plus 3, which is, okay. So this is my linear combination. Can I actually, next gray shirt, can I perform this operation, the second one?
No, because only one is in vector form.
Right. So essentially, these are technically a scalar is a vector with only one element, right? So basically, I have two vectors of mismatching size, so I can essentially not perform this operation. Okay. So, and then my next last gray shirt. So I can ask you again. Hi. Hello, join us. So basically, what do I, the last one? Can I perform that operation?
2 by 1 plus 1 by 2.
So I have enough elements. I could kind of force it if I had to, but formally, this is a column vector, this is a row vector. Their dimensions are formally different. Actually, we're going to get to matrices in a moment, but this is a 2 by 1 matrix, and this is a 1 by 2. Okay? So the total number of elements in both are the same, but I cannot perform this last operation. So trying not to text in classes, use all other devices. Also try not to use your computers for anything other than classwork, which right now basically is just maybe following this PowerPoint when we get to using MATLAB. So of course, if you want to follow the PowerPoints that I post lectures, you can. But for your own good, if you're now in class, may as well be in class and try to retain as much material so that it's easier later. It is hard to resist the draw of internet and constant emails and texts and Facebooks and Twitters and whatnot, but for your own benefit, in order to do better in classes in general, just since you're sitting here, may as well work on examples, and that will not prevent me to call on you and ask you for for opinion. Yes?
Why would we record something? Since they're both one-dimensional, or since they're both one-dimensional vectors, why would you make one of them a column and one a row? Like, what informs that decision?
So in this particular case, it's not obvious, but in general, I actually have to be able to, so these are still in general matrices, and matrices will have certain dimensions based on how I design them. So if I'm designing them, then I have to be careful so that I can formally operate them as matrices and do matrix multiplication later.
So it depends on the problem.
So if you were designing something, you were in charge, so you can design them one way or the other. But mathematically, rules should be clear. Okay? So 2 by 1 and 1 by 2 are different. Okay, mathematically. And mathematically, and also computers can follow only clear instructions. Okay? And computers also have certain set of rules, and for them, you recognize that these are necessarily the same. Computer might have harder time. Okay, so here is one case where it really matters. That is the inner product. So if I have two vectors, to formally do inner product is defined as a matrix multiplication, to which we are going to get to in a moment. And to be able to process these as matrix multiplication, the first one has to be a row vector, and the second one has to be a column vector. But formally what I'm doing is I'm saying I'll take x1, y1, plus x2, y2, plus x3, y3, plus x4, y4, and so forth if they were longer. Okay? So basically, yes?
So that sigma notation right there, does that only work because you're multiplying a one-dimensional by another one-dimensional?
Yes.
So if you make that two-dimensional and you want to add or express it in terms of the sigma notation, would you add another sigma notation? So instead it would be like I equals 1 to n, and then like j equals 1 to n, and it'll be like x, I.
If I had vectors of different lengths, I wouldn't be able to do this. So they have to be of the same length. Great point.
Okay.
So I have to have two vectors that have the same number of elements
For that notation.
for this operation to work. Now the sum in itself, if I'm just doing this sum, this works regardless of whether they're column vectors, row vectors. They could be both column, both row, both, right? One of them row, one of them column. But this definition is actually in terms of matrices. Okay? And for this, I have to have them precisely in this form. And we'll get to the matrix multiplication, so it's going to be clear why. Okay? So basically, technically, I can always compute this as this part, the first part, the sum part. I can always do regardless of the type of vectors. Formally, I will assume that both of my vectors are column vectors, and I'm going to do x transpose times y. Okay. But that's just so that we can actually, in terms of program operations, we can actually pass it along as matrices. Okay. Questions? As long as I have essentially two same vectors, I can do this operation, and this is called vector inner product. The result of this operation is just a number, just a scalar. So I took two vectors and I made a scalar out of it. Now I also could do a vector norm. Okay, so technically if I have two scalars, 3 and 7, I can compare them. So I know that 7 is larger than 3. Now if I have rows or columns of vectors, I'd like to be able to do the same. But it's extremely difficult to do that because I have way too many numbers, and I would just like, oh, well, is this larger or the other? Okay? So for that, we will actually define vector norms, and vector norms will enable us to compare vectors. So essentially, in scalars, I could just go with absolute numbers, absolute values, and equivalent of the absolute value will be vector norm, and I'm going to define it in a moment. I will define a number of norms. Okay, so there are no clear one norm that I could use, and again, it will depend on my application which one I will like. But all of the norms have to obey subsensible rules. If I have a unit vector, it will have magnitude 1. And if I have a zero vector, no matter which norm, the norm of a zero vector that has all zeros, should be 0. Okay, so if I have a vector of all zeros, its norm should be 0. Yes?
Why would you ever use the function of a zero vector?
Huh?
Why would that exist?
0 in general is a number that you add to any other number, and that number remains the same. It's useful in any kind of operations when you do mathematically. It's useful to have that. Okay? So if I have a zero vector, I want that vector to be also of zero norm, so that it's kind of it's normalizing my scale. Okay? So when I'm comparing different numbers, it's normalizing. It might be that you will actually get a 0 as a result of operation, and 0 means nothing's happening, so it has a clear meaning. Okay? Yes?
I think another way to say it would be that it's also a placeholder for if you want to add two vectors and not the same magnitude, so you can possibly use it as a placeholder to equalize their magnitude.
Yes. So sometimes, yes. Okay? It could be that I have, and let's come up with a petroleum engineering equivalent of this. You have one well and you drilled it to 5,000 feet. Okay? And you're moving over nearby, and you presently actually don't know whether you're drilling to 5,000 or 5,300 feet. Okay? So basically, you will still like to compare these two wells, for instance, porosities and so forth, matching the depth, because they're relatively close, so you would like to, whatever you learned on the first well, you would like to apply to the other. So you'd like to compare them, right? But you might not have enough length at the very bottom, right? So one of them you will just add zeros in order to mathematically process on a computer. Make sense? So you will just adjust as necessary, so sometimes it's a placeholder indeed. Now, let's see what these norms should be. So if I have one of the famous vectors is a velocity. If I have a velocity, I have certain speed, I'm running with certain speed, but I also have a direction. I could be running in this direction, or I could be running in the opposite direction, right? So velocity in itself is a vector, okay? That vector has a clear direction, and it also has length that is the magnitude. So speed is actually the magnitude of the velocity vector, its length. And if I had a two-dimensional space and I have a velocity vector, in this case it's 3, 4, right? So it's what I typically refer to as 3i plus 4j in geometry. Then the speed is square root, basically this is Pythagorean, oops, can somebody say that in English for me? Pythagorean? Yes? Say it,
No,
please.
I'm done.
I always mess it up. So, any English speaker, can you say? Thank you. Okay. So, based on that rule, I'm gonna find the length of 5. The problem with Pythagoras is that in my own language it's Pythagora, and the moment I see it, I want to say in Croatian, and that connection is hard to break. Which is the same reason why I say pi and p all the time. Okay. So basically this is 5, okay? So this is actually the basis of one type of norm, and we will refer to this as Euclidean, because it's a Euclidean distance, goes back to Greek times because Euclid came up with it, or also L2 norm.
Wait, so speed is the L2 norm, or just the idea of taking the square of each part?
Yes, so L2 norm will be the generalized Euclidean norm. So Euclid worked only in 2D and 3D. Okay. So for two-dimensional and three-dimensional vectors, those would be the Euclidean norms.
Okay.
But when I actually define them for any type of vector, I'm going to call that L2. for all intensive purposes, these can be used interchangeably, okay? So essentially, how will I define this? So this is my Euclidean or L2 norm. I will take a square root of squares, sum of the squares of all elements, okay? So basically, you can do that for if I had n members or n elements in my array. I would square each one of them and basically take a square root of that sum. And this can be basically expressed in terms of that inner product. So this is the same if I had a column vector as taking x transpose, which is a row vector, times x, which is a column vector, which is what I had on the previous slide. Okay. So basically, if I had x1, x2, x3, x4 here, I would get x1 squared, x2 squared, plus x3 squared, plus x4 squared. Now, you might be wondering, why on earth would I introduce you to this? Okay. There's a whole lot of linear algebra theory behind this that makes operations on matrices and proving theorems a whole lot easier because I have this definition. We are not going to go through those theorems, but if in your, for instance, graduate studies or sometimes later you get introduced to those, you will know what they mean. So there's a whole lot of theory that is made so much easier just because of this definition, even though you're looking at it and like, why didn't you just put that sum over there and be done with it, right? So I'm introducing you to notation that you might come across later. Okay? Yes?
When do we use the double bar for the norm, and when do we put the subscript 2?
So this will be clear in a second. So this 2 clearly states that this is L2 norm. Okay? If there is some doubt and I'm possibly using another norm, then I will put a different number here. Okay? So this 2, if it's clear from whatever problem that you're working on in a specific norm, you don't necessarily need to add this 2. But if there might be confusion, then you want to be clear. Okay. So why are norms in general? Oh, let me introduce this. What are these other norms, possibly? So I can just generalize this concept of 2 norm to any number norm. Why not use, that's what mathematicians do. Why not use 3? Why not use 4? Why not use 5, right? And it really works. From the theoretical standpoint, you can use any P, okay? And any P norm is defined as this sum of absolute values to the P, okay? And then I take Pth root of that sum, okay? So that works. We will mostly work with L2 norm out of these interesting ones, and L1 norm. So this is really the simple one, where I just take sum of absolute values. Okay? And there's one norm that is kind of odd, because we cannot formally take that formula for infinity, but an infinity norm is actually defined as maximum of all of the absolute values. So there's obvious use for this in any kind. So sometimes I'm just wondering, what is the maximum if my entries are pressures? What is the maximum pressure that I had? Okay, because I might want to check whether my equipment is rated for that pressure. Right? So there's obvious use for this norm in certain cases.
How is it different than the L1? How is it different than the L1?
This is maximum of the number. Great question. So compute all these 2 norms for x is 1, 2. Do I still have gray colors? So can you actually compute 2 norm for the vector 1, 2? I have a vector 1, 2. What is my 2 norm? So if P is equal to 2, I will take x1, which is 1, right? So x1 squared, which is 1, plus x2, which is 2, squared, which is 4. Okay? So 1 plus 4 is 5, and then I'm going to take that 5 to 1 over p, and p is 2, so that's square root. Okay? So square root of 1 plus 4 is square root of 5. So that is my L2 norm of this particular vector. Now what is my next gray shirt? So what is my L1 norm of this vector? 3, because I took 1, x1, absolute value, so that's 1, plus absolute value of 2, sum of that is 3. Okay? And then finally I have this value, where is my next gray shirt? So what is the L infinity norm of this vector? 2. So it's the maximum between 1 and 2. If I had minus 2 here, it would still be 2 because absolute value of that is 2. Okay? So I'm discarding any kind of negative entries. So do we see the difference now between 3 norms? So they measure different things. Now again, why is this measuring different things? Why is that useful? Okay. So for any kind of comparisons and decision making. So first, you need to agree ahead of time what is the norm that you're going to compare things with. So for instance, in Austin, stage 2 watering restrictions are activated when combined storage levels of Lakes Travis and Buchanan drop below 900,000 acre feet. So if I had a vector with 2 entries, that will constantly, in first entry there will be Lake Travis, and the second entry would be the storage level of Lake Buchanan. Okay. Then L1 norm of that vector would give me the combined storage level. And I would just take, well, is that L1 norm of that vector, did it drop below 900,000? And now I can actually program that. So if I have continuous, typically these measurements are coming in continually, and you can actually go and look at them online. Okay? So you can program for that sum to alert somebody, some engineer on the job, hey, hello, this level has dropped below the critical level. So this is basically an example of using L1 norm. So this is essentially the stage water 2 restrictions, and if you find somebody violating the watering restrictions, you actually call 311. All right. Now there's another place where L1 is much more useful. So typically we think of, in terms of measuring distances, we like airplane distances, right? So distance between this point and this point is basically just length, which is Euclidean norm of that vector between those 2 points. Well, depends where you're at. Let's say that you're on a city grid. Imagine that this is some very regular city, and you actually need to plan gas from going to point A or point 2, or you need to plan how long it will take you. Airplane distance means nothing unless you can actually fly, and none of us can. So actually to come up with distances, you actually have to sum up all of these values. And that basically comes down to some L1 norm, not L2. Because for instance, if I had this vector 6 minus 6 from here going to here, if I had a vector that was pointing in this direction, then essentially my L1 norm would be 6 plus 6, which is 6 times going down and 6 times going to the right? Which is 12, and that's an actual distance that I would be walking to this, whatever this unit 1 is, 1 building, 1 block. Okay. So I'd be going 12 blocks, whereas L2 would give me 8.5, which is quite much less than 12. So again, this L1 norm is much more useful than it looks like. Alright? So basically, different norms measure different things. And one point, there's a whole lot of text here. But if I had, there are much more complicated situations. If I had basically a vector of porosities, and I want to sort of accentuate small entries, then those small entries, let's say that I have 0.1, 2, and 30, this 0.1, if I just take the absolute values and sum it up, will give a bigger contribution to the norm than it would if I actually did the 2 norm, so I took square of 0.01 and square of 30, those become much further apart, and a smaller number kind of drops out. Because compared to 900, 0.0001, when you sum them together, you don't get much. So basically, small numbers get lost when I'm taking 2 norm. And if I want to accentuate them a little, I will use L1 norm. And that might, in your particular application, make you decide which of these 2 norms you should use for your own purpose. Now, if you have that maximum, so L infinity norm is sometimes called maximum norm. That one is, of course, useful for the worst case scenario. What is my largest pressure? What is my smallest this? Smallest, largest that, right? So that one, sometimes a situation calls for this max norm, and that's what you're going to use. All right. So I think this is we're gonna stop for today, and we're gonna continue on Wednesday.